Okay, so here's example 2, and we're given this matrix T, and to diagonalize this matrix, we take T as a representation of a transformation with respect to the standard basis. So we're going to take this, okay, with respect to the standard basis, which is going to be E2, or epsilon 2, sorry, of T. Okay. So we start with the fact that, again, that it represents a transformation with respect to these bases. And then we want to look for a basis B, right? So we want to look for a basis B, beta 1, and beta 2 in this case, oops. Right? Such that we get what? Such that we have that. So in other words, such that we have those two relationships. So how do we do that? Well, just like from before, we set up our products, right? So we're going to take 3, 2, 0, 1, take our matrix, times what? Times each of the bases, right? So this will be beta 1, right? Okay? And we want that to be equal to lambda 1 times beta 1. And the same thing over here. So we're going to take our matrix 3, 2, 0, 1 times beta 2 vector equals lambda 2 times our beta 2 vector. So we're looking for scalars x such that this equation holds. It has the solutions B1 and B2. So, here, oh, how do I want to do this? Yeah, so here, if I erase this, we can look at it this way, so, and we just put an X here. And so we're looking for scalars x such that that equation holds. And has solutions b1 and b2 that are not both 0. That's the key thing, right? We don't want them to both be 0. Because remember, the 0 vector is not the member of any basis. So that's a linear system. So how do we set that up? Well, set it up like we normally do with a linear system, right? So that's going to give us what? It's going to give us so if we set up the linear system, that's going to give us okay, right? And so what this is going to give us is, how do we want to do this? This is going to, yeah, so if we move everything over, what do we get? So if we move everything over, we get, yeah, so let me rewrite this. So that this will be 3 minus x. Yeah, so it'll be 3 minus x times b1 plus 2b2 is equal to 0. And this one here will just be, well, this goes away. So this is going to be 1 minus x. Is equal to, times b is equal to 0. Okay, so that's what our system becomes. Now we're going to focus first on the bottom equation. There are two cases. Either b2 is equal to 0 or x is equal to 1. If the b2 is equal to 0 case, if b2 is equal to 0, the first equation gives that either b1 is equal to 0 or x is equal to 3. Since we've disallowed the possibility that both b2 and b1 are equal to 0, then we're left with the first diagonal entry, lambda 1, equal to 3. Okay, do you see that? Let me say that again. If we look at the bottom equation, right, if we look at this here, focus on this first, then the only options we have is either b2 is going to equal 0 or x is equal to 1. That's the zero product principle, right? That goes way back when. This is elementary, right? The zero product principle says either this is going to be 0 or this factor is going to be 0, which means b2 is equal to 0, or this is equal to 0, which means x has to equal 1. Okay, so those are the only two possibilities. Now, if b2 is equal to 0, then that gives us two possible answers for the first equation. Okay, because if b2 is equal to 0, this goes away, and we end up with what? The case that either b1 is equal to 0 or 3 minus x is equal to 0. But again, if b1 is equal to 0, well, we've just said that b2 is equal to 0. So they both can't be 0 because, again, we can't have both zeros along the diagonal. Okay, so that means that x is going to be 3. Okay? And so, again, we are left with the first diagonal entry as lambda 1 equal to 3. And with that, what do we get? And if that's the case, what do we get? We get 0 times b1 plus 2b2 is equal to 0. And so associated with lambda 1 equal to 3 are vectors having a second component of 0 while the first component is free. Right? Because if we're saying this is equal to negative 1, let's see here. Yeah. So we end up with this. Oh, here, I'll just do it here. Yeah. So excuse me, I'm sorry. Okay. 3201, does that give us where? Oh, and then of course, that's 3. Like so. And to get a first basis vector, choose any non-zero b1. For example, we could have beta 1 equal to 1, 0. Now the other case for the bottom of equation, so again going back to here, the other case for the bottom equation is to have x for the bottom equation is to have lambda 2 equal to 1. And then the first equation is going to be 2 times b1 plus 2 times b2 or excuse me, x equals 1. So the other case is they have x equal to 1, which means this equation on the top goes to 2 minus 1, which becomes 2 times b1 plus b2 is equal to 0. Okay? So what happens in that case? So that's going to be associated with this case are the vectors whose second component is negative the first component. Because what happens here, if this is 2, right, and it's equal to 0, then these have to be opposites of each other because the 2's cancel out. We can factor that out, and that doesn't really matter. We can divide the whole thing by 2, and it doesn't matter. So we get b1 is equal to negative b2. Okay, so that's the result of that one. Okay, so then what do we get? Well, then we get, instead of this, we get this, and we get 1, and this is negative b1. We get that set up. And so get the second basis vector by choosing a non-zero one of these, right? So now we just have to choose a non-zero one of these, which the simplest one is just to do 1, negative 1. And so now our matrix becomes what? Think about it. So now if we set up our matrix with beta 1 and beta 2, we get 1, 0, 1, negative 1. So guess what? That's the matrix we're going to use. And so the matrix, the representation with respect to B, basis B, and epsilon 2, identity map is easy giving this diagonalization. So, let me do this. Let me erase this. And I'll put this here. So if we do 1, 1, 0, negative 1, inverse, 3, 2, 0, 1 times 1, 1, 0, negative 1. And so if we compose this, right, and again, I'm going to leave you to do this. It'll be good practice, but compose this right to left, and you'll get this diagonal. Now, it's not a surprise that they turn out to be 3 and 1. Okay? And that's it.